Right, recorded is rolling. Welcome to Tuesday, March 29. So we're going to review, this says sum of momentum initial equals sum of momentum final. That's momentum conservation, maybe specifically for a closed system, right? If there's no outside force acting on a system. And so conservation of momentum is mass times velocity. It's usually involved in collisions. Anytime you see a collision, think this framework right here. Okay? Unless, of course, something is colliding with a spring and the spring has negligible mass, then just go straight into energy conservation. But otherwise, you want to do this. Okay? Guys, this formula right here is called what formula? Starts with an I. Impulse. Yeah. Guys, impulse, that's a change in momentum. It might be like mass times change in velocity. And if something is changing its momentum, that's because there's a force applied. So force times time interval. So anytime you see a graph that has force and time axes, there's probably going to be an impulse type question. Okay. Oh, force versus time graph. Okay. So we'll review all that. I want to remind you guys too, upcoming due dates. So there's an AP classroom unit 5, multiple choice questions part B due pretty soon. Let's bump that to Friday because rearrange a little bit of stuff in the schedule. I'm going to do a couple of FRQs with you guys next couple of days. So we'll cover this on Friday. So just have this done by then. Right. And then you guys remember also you have a Unit 4 or 5 review quiz due a few days from now on Monday. I come back from the weekend. Oh, you know what? Should have this ready to go. You guys remember yesterday we were doing energy conservation? I have one more energy conservation we're going to do. It's the roller coaster. Now, you guys know the answer to this because at least I remember the answer to this yesterday. But I want to see if you guys can derive this from scratch. Okay. So I got this roller coaster that starts at the top of a hill. It's going to go around this loop. Now, let's say that this loop is approximately circular. It has a radial size R, fixed radial size. Call that approximately a circle. And we want to make sure that the roller coaster gets around the loop. And let's say that there's negligible friction, so you don't have to worry about frictional losses. And the question is, what is the minimum height that you'd have to drop this roller coaster from so that just under the influence of its own weight, it's able to get around that loop? So I'll call this H min, right? Like minimum height, right? What is that height? Okay. Because, for example, I know if that height was equal to 2r, which would be just take this line, just dash it straight across, right? Wouldn't this height be equal to 2r? You guys see that? R plus r, diameter of that circle would be 2r, right? If you started the cart from that point, would it be able to make it around? No, because here's what would happen. It would lose potential energy, gain kinetic, right? And then going up the side of the curve, it would lose kinetic, gain potential. But then by the time it reaches the same point it started, same height, it would run out of kinetic, which means to have zero velocity, which means it would fall off the track. So it just needs some minimum speed to get around. And maybe that's one thing that might help you frame this question. There's some V minimum to get around. Okay. All right. So give you guys a couple minutes head start. Actually, I will pause this recording. So if you're watching this recording at home, you're going to pause this for a minute. Go ahead and pull out a piece of paper at home and see if you guys can prove what the minimum height is if there's negligible friction. What's the minimum height if that starts from rest? All right, recording is resumed. All right, so you should be able to get the minimum height as some multiple of this radial size, and you know it has to be bigger than 2r, right? So we figured out that much anyway. So you do need conservation of energy to solve this, but you actually need to go back to unit 2 and look at free body diagram of this cart at the this vulnerable position here. Because if it makes it past this point, then it's all in the clear. Okay, guys, what's a good free body diagram vector, force vector to put on this cart right here? Yeah, possibly a normal force. Now, if there's a normal force from the track, which way would it push? Down, right? Oh, is there another force that also acts down? It's weight, right? You're like mg, it's weight, right? Actually, that would be a good free body diagram. Have two force vectors that both push down, right? It's weight pushing down, and probably also a normal force. I mean, especially if you want like a factor of safety, I better put also a normal force down, right? And so there would definitely be a net force downward on the cart, but that makes sense because the fact that it's on a curved path. So as it's moving to the left, it's also being pushed down at the same time, right? You guys see it put on a curved path. Now I'm going to leave off the normal force. Why am I doing that? Because I'm specifically looking for the boundary condition of where it just barely gets around. So what if that normal force like shrinks to 0? You guys get that? Right? Although that would normally be a good thing to also include in your free body diagram. Right, so I'm thinking this, that the net force would be the weight of this thing. Okay. There's so guys, the fact that it's on a curved path means that that net force, which could be the weight plus the normal, but take a normal to 0, okay, also represents what kind of force? Starts with the C? Centripetal. So wouldn't the centripetal force be represented by just the weight if you let the normal force go to 0? Okay. Normally I say like plus normal force. Okay. And centripetal force, we have a formula for that. What's that formula?
mv squared over r.
mv squared over r. Okay. You could also say m omega squared times r, but yeah, we're definitely doing this one. Mv squared divided by r. We're using that, playing off that linear speed. Okay. Oh, do you guys see you could solve for the minimum speed right here? Okay. Right here. Okay. And I know it's the minimum speed because I let normal force go to 0. Okay. Oh, what's going to cancel out on both sides? The mass. Okay. So whether it's an empty cart or if it's full of passengers, that makes no difference to the outcome. Okay. You guys see that v squared, it's going to be g times r. And then if you wanted the v minimum, that'd be the square root of gr. Right, you guys see that? Okay. Okay, so it does depend what planet you're on, and it also depends on the size of the that loop. Okay. Now that's not the answer to the question. The ultimate question is what's the minimum height drop? Okay. But this is an important middle step. Now let's go to the actual minimum height drop. That's going to involve conservation of energy. Sum of energy initial equals sum of energy final. Okay. I can say this for a closed system. Now, if this is a closed system, what do you for sure have to include in that system? The what and the what? The cart and the earth. Yeah, this could be the cart earth system, right? Cart earth system. Okay. So starts off with, I'm thinking potential energy, mgh. Okay. Let's let this be h minimum because we're solving for that. I mean, the whole framework of this. And then now if I call it h minimum, it looks like I'm defining this dashed line down here as height 0. So whenever you use mgh, you have to define some floor somewhere and then some height 0. So it looks like I'm defining height 0 as like down at this dashed line. And as long as I'm consistent throughout the problem, then it's all going to be okay. So in my second point, got initial to final, does the cart have any potential energy here?
Yeah.
Yes, it does. Guys, what is the height of this cart at this point?
2r.
2r. Is everybody seeing that? Are you guys seeing this step ahead of me? You guys are going to beat me to the answer, right? Okay. You guys see that it does have some mg times 2r worth of potential energy, and there's some energy left over, which is a good thing because that's going to go into its speed and as kinetic energy, 1/2 mv squared. Guys, that good conservation of energy for that setup. Okay, true. Okay. Right, and we're trying to solve for this. Okay. Now, okay. mg, I know that there's some generic r I can leave there, but I know there's also some minimum speed it needs to get around. Maybe that v, but I already took care of that. We did that with the free body diagram and centripetal force. I could either sub this in there or I could sub this in there. Actually, I'm just going to play off this stuff right here. V squared is equal to gr. You guys see that? Okay. So that's going to be this right here. That's just going to be gr for the whole v squared. You guys see that? So the next step is going to go mg h minimum turns into, well, I'll slide this to on front. I don't know, why not? 2 mgr plus 1/2 mgr. Right? That's all energy terms. I have 3 terms and they're all energy terms. What's going to cancel out at this point? Mass and gravity field. So not only does it not matter if you have empty carts or carts filled with passengers. By the way, anytime you just go from gravitational potential to energy to kinetic or back and forth, it's really common for mass to cancel out. But also the gravity field cancels out. Now think about what that means in physics. That means that it doesn't matter what planet you do this experiment on. You could take this up to Mars and whatever the answer is, it's going to be the same answer. Kind of makes sense that should be the case, right? H minimum is 2r plus 1/2 r It's 2.5 r. You could also call that as an improper fraction. 5 has r. Okay. So where would that be on this picture? Well, there's r, there's 2r, 2.5 r is probably right about here. Okay. 2.5 r. There's your answer. All right, so that's again last conservation of energy from yesterday. All right, you guys ready to go on to conservation and momentum?
Yeah, actually.